welcome to the fourth lesson of module 2, which is on analysis of strain part 4. In the previous lesson, we have discussed some aspect of analysis of strain, and in this particular lesson, we are going to discuss some more aspects of strain analysis, and let us look into those aspects. Well, after completing this particular lesson, it is expected that one should be able to understand the concept of strain due to change in temperature. We have discussed the aspects of strain in our previous lessons, and we have seen how to compute strain at a point in a body and in a member when it is subjected to axial pull. Today we will be discussing some aspects of development of strain due to change in temperature. Also, one should be able to understand the concept of thermal stresses, and we have discussed in the last lesson about the determinate and indeterminate systems, where we find that we need additional criteria to evaluate the internal forces, which we have termed as compatibility condition. Now, we will be looking into some more aspects of this indeterminate system, and one should have a clear idea about the indeterminate system. Well, this particular lesson includes recapitulation of previous lesson. As usual, we will be discussing the questions which I had posed last time, and through those questions we should be in a position to go through the aspects which we have discussed in the previous lesson. Well, it is evaluation of strain in a body due to variation in temperature. We will be looking into that. Then concept of thermal stresses and indeterminate system, that whether this change in temperature, the strain which is caused due to change in temperature, whether there is a determinate one or indeterminate one, and subsequently we will evaluate the stresses due to change in temperature in different systems. Well, let us look into the answers to the questions which I had posed last time. Now, the question which was posed is, what is meant by indeterminate system and how is it different from determinate ones? Well, in indeterminate system, the number of unknown forces, they are more than the number of equilibrium equations available, and those kind of systems we generally call as statically indeterminate system, where the number of unknown forces are more than the number of equilibrium equations. We have seen what is meant by equilibrium equations, and for the solution of such systems we have seen that we need additional criteria to be brought in so that we can evaluate the unknown forces. And the way it differs from the determinate system is that if the equilibrium equations are adequate to evaluate the reactive forces or the internal forces, we call those kind of system as determinate one, and this distinguishes between the indeterminate system and the determinate system. Well, the second question posed was, what is meant by compatibility equation? Okay, let us look into this definition of compatibility. As we had seen last time, that a statically indeterminate problem has geometric restrictions always imposed on its deformation, and the mathematical expression of such constraints or the restrictions are known as the compatibility equation. Now, probably this can be made more clear through an example. Let us look into this particular example, which is quite common. You must have seen that the vertical members made out of concrete are provided with some steel bars. If we cut a cross section, if we cut a section here and look from the top, then the section looks like this. Let us assume that the cross section of this vertical member is a square one with the sizes of the sides as A. Now, this particular cross section of the member is provided with 4 steel rods. Now, a bearing plate is connected to the top of this member, and it is subjected to a load P onto top of the plate. Now, if we take a free body diagram, if we cut the member here and take the free body of the top part, the free body diagram looks like this, where the top force is P, and for the equilibrium of the whole system, we will have the forces generated, internal forces, which will be exerted by the concrete, let us call that as PC, and the steel rods in a combined form, let us call that as PS. So, the equilibrium condition demands that P should be equals to PC plus PS. Now, as you can see here that we have 2 unknown parameters PC and PS, and we have only one equilibrium equation. Hence, the 2 unknowns from one equation cannot be evaluated, and hence we need an additional criteria or additional condition, which we call as a compatibility criteria. As we have seen last time, that the deformation, when we put the restrictions on the deformation and convert that in terms of mathematical expression, we call that particular condition as the compatibility condition. Similarly, here, now when the load is applied onto this member, the deformation of the concrete and steel, these two different materials which are placed in this particular diagram or in this particular member, the deformation of concrete and the deformation of steel should be same. So, if we say that the deformation of concrete is delta C, this should be equals to deformation in steel, or in other words, we can say the strain in concrete is equals to the strain in steel. And this strain, as we had done last time, now the strain we convert or write in terms of stresses using Hooke's law, which we call as the constitutive relationship between the stress and the strain, and that will give us another condition for forces between the concrete and the steel. Now that we have one equation from here, we get another equation from here, and using these two equations, we can solve for PC and PS. So, this particular condition, that P is equals to PC plus PS, is termed as equilibrium equation, and another equation in terms of forces which are generated from the second of equation, where strain in concrete is equals to strain in steel, we call this as compatibility equation. This we call as compatibility equation. And as you can observe here, that the restrictions on the deformation, we have said that the deformation of concrete and deformation of steel is same, and based on that, this compatibility criteria has been arrived at. Now, the third question which was posed was, what will be the effect of temperature variation in a stress system? Now, this is the aspect which we are going to discuss about. Now, strain due to temperature. Now, it is known that if a body is subjected to temperature variation, then it undergoes changes in its dimensions. is volume expands if there is an increase in the temperature, or it contracts if there is decrease in the temperature. Now, in general, this change in temperature, if the temperature is uniformly increased or decreased, we get same amount of expansion or contraction in the body, and this is isotropic in nature, and that variation in temperature causes change in the length of the member, which we call as deformation, and that deformation leads to strain in the body, and strain due to variation in temperature is given by this particular expression epsilon t, where is the epsilon t is the strain due to change in temperature, delta t is the change in temperature. Let us say if the initial temperature is T suffix 0, final temperature is T, then delta T is equals to T minus T 0, and alpha is a term which is known as the coefficient of thermal expansion. So, the strain due to temperature variation is given as alpha times delta T or T minus T 0, and delta T is positive when we take there is expansion or there is a positive change in the temperature, where there is a rise in the temperature, we call delta T as positive. When there is a decrease in the temperature, we call that as negative or for contraction of the body. Now, uniform change in temperature throughout the body causes uniform thermal strain. Now, this is important to know that there is strain which is developed in the body due to change in temperature, we call that as thermal strain. Now, supposing there is a body which undergoes change in the temperature. Now, if it is free to move, this will undergo expansion or contraction depending on the change in the temperature. If temperature rises, it will expand. If temperature decreases, then it will contract. Now, if it is not restricted or constricted by any actions from outside, it will undergo movement, it will undergo strain. Now, if we take the characteristic length of this particular member as L, or for that matter any of this length which undergoes deformation, the deformation delta T of that length can be given as the strain times the length, and strain, as we have seen, due to temperature as equals to alpha times delta T. So, the deformation delta T because of temperature is alpha times delta T times L, where L is the dimension which we are concentrating on of the body. Now, if the thermal deformation occurs, as I was telling you, that if it is allowed to move freely, then there is no possibility of inducing any stress in the member. Now, as there are no internal forces are developed, no internal forces are induced if thermal deformation is allowed to occur freely. Now, there will be strain induced, but there will not be any stress in the member, as there are no internal forces are getting developed. So, naturally there will not be any stresses, but since it is undergoing deformation, either it is expanding because of the change in the temperature or rise in the temperature, or it is contracting because of decrease in the temperature. So, there is movement, there is deformation, in turn there is strains, but since it is not restricted, the movement of the body is not restricted, as no internal forces are getting generated, and hence there will not be any stresses in the member. So, that is why it says that strain will be induced, but no stress will be developed. Now, total or partial restriction of deformation induces internal forces. Now, if this particular body which is free to move due to change in the temperature. Now, supposing if I hold this body from two sides and do not allow this to move, since it will try to expand, it will exert pressure on this support, and as a result the body will be subjected to some internal forces, and thereby there will be stresses induced in the body. So, if total or partial restrictions are imposed on these deformations, then they are going to resist these forces due to thermal expansion or contraction, and thereby there will be stresses caused by these internal forces, and these stresses we generally designate as thermal stresses. You must have noticed that in many a times in structures we provide a gap between two structural elements. Now, we allow the structural member to move, expand or contract due to the variation in temperature. You must have noticed in the railway tracks are not continuous. Some gaps are maintained at certain distance interval. Now, due to change in the temperature on the railway track, the track undergoes expansion. Now, if those gaps are not kept, then the rail track will be subjected to tremendous amount of stresses. Well, the forces developed due to temperature change, the change in temperature causes forces if they are restricted, and these forces cannot be determined from equilibrium equations as we have seen earlier. So, since we cannot determine the internal forces which are getting developed due to change in the temperature, so we call these kind of systems as indeterminate system according to the definition as we have seen earlier. Now, for the systems for which we can evaluate the internal forces based on the equations of equilibrium, we call those systems as determinate one. But if we cannot evaluate the forces which are getting developed due to change in the temperature from the equilibrium equations, then we call these systems as indeterminate one. Hence, this kind of the thermal stresses which are induced in the member are basically statically indeterminate, and we need to use the equation of compatibility for the solution of these forces for evaluating the internal forces. Well, then if we summarize on the statically indeterminate problems which we have seen now, that we need the equilibrium conditions. The equilibrium conditions has to be satisfied, and that is either in a local concept or in a global sense for the whole structure. So, equations of equilibrium has to be satisfied. Secondly, the geometric compatibility has to be satisfied if we get more number of unknowns than the number of equilibrium equations available. So, they are known as compatibility condition as we have seen, or correspondingly compatibility equations, which gives us additional information based on which we can solve the unknown forces. Thirdly, that we have written down the compatibility in terms of the geometric deformation, and we have related the strain parameter to the corresponding stress parameter using Hooke's law, and this relationship between the stress and the strain is generally referred as the constitutive relationship, which in this case is based on Hooke's law. We are arriving at the constitutive relationship. So, these three are the essential parts for the solution of statically indeterminate problems. First one is equilibrium equation, second one is compatibility equation, and third one is the constitutive relationship, which gives us the relationship between the strain and the stress, and thereby we can write down the equations in terms of forces. So, we have one equation which we have written in terms of equilibrium criteria, we have another equation which we are writing in terms of compatibility criteria, from which we can solve for unknown internal forces. So, solution of equilibrium and compatibility equations for unknown forces using equilibrium and compatibility criteria. Well, having known about these different kinds of strains that is getting induced into a body, either when they are subjected to external loads or they are subjected to change in temperature, let us look into some of the examples that how do you evaluate these forces. Now, last time I had set one example for you which I had asked you to solve. Let me discuss that particular problem first before I proceed further with other problems. Now, the example which was given was that the rigid bar AB, this bar AB of negligible weight is supported by a pin at B and two vertical rods, they are hung from the top and connected to this bar. Find the vertical displacement, of the 50 kilonewton weight which is placed at this particular point, which is at a distance of 1 meter from end A. So, we will have to find out the displacement of this particular point where this 50 kilonewton weight is hung. The cross sectional area of steel bar is 300 millimeter square. This is the steel bar of length 2 meter and this is the aluminum bar of length 1 meter. The cross sectional area of steel bar is 300 millimeter square and that of aluminum is 1000 millimeter square. The modulus of elasticity of steel E suffix s is 2 into 10 to the power 5 megapascal and modulus of elasticity of aluminum is 0.7 into 10 to the power 5 megapascal. So, we will have to find out the displacement, the vertical displacement of this particular point from where the 50 kilonewton weight is hung. Now, as we did earlier or as we discussed, that first thing is that we will have to write down the equations of equilibrium. Now, if we take the free body of the whole system, this is the bar, rigid bar AB, and this is connected by a pin at end P. We have one vertical rod connected at this end, we have another vertical rod connected at this end. This is made of steel, this is made of aluminum. Let us call the force in the aluminum rod as P aluminum and the force in the steel as Ps, and the 50 kilonewton load is hung from this point, which is at a distance of 1 meter. This is 1 meter, this is 1 meter, this is 1 meter. This is 50 kilonewton. Now, if we write down, now if we take off even this pin part of it, we will have the reactive components, the vertical force and the horizontal force. Let us call this as R and H. Now, since we do not like to evaluate R and H, we are interested in PS and PL because we would like to find out how much force these rigid rods will be subjected to. Now, let us take the moment of all these forces about point B. So, summation of all the forces with B is equals to 0. This is one of the equilibrium equations, and this gives us that P aluminum times 1 plus P steel times 3, this is equals to 50 times 2, or P aluminum plus 3 P steel is equals to 100. So, this is equation 1, which we call as the equilibrium equation. This is the equilibrium equation. Now, well, we are not looking into other equations which are summation of vertical forces as 0 and summation of horizontal forces 0, from which we will get R and H. We are since we are interested to evaluate only this, because we have 4 unknown parameters Ps, Pal, R and H. These are the 4 unknown forces, and we have 3 equations which are summation of horizontal forces 0, summation of vertical forces 0, and summation of moment at this point is equals to 0. Now, this particular equation, as we see that we have 2 unknowns and 1 equation from which we cannot really solve these unknown forces. So, we need an additional criteria or additional condition from which we can evaluate these forces. Now, if we look into the deformation of this member, this particular bar AB is a rigid one. Now, since this is subjected to a load 50 kilonewton, this will undergo a movement in a circular path, considering point B as a center. Now, since the deformation is small, this circular arc we approximate as a straight one, and we join this line. This gives us an exaggerated form of the deformation. So, this point undergoes deformation here, this point undergoes deformation here, also this point has deformed up to this state. Now, from this triangular configuration, if we call this deformation as delta aluminum and this deformation as delta S, then from this triangular configuration we can write delta aluminum by 1 is equals to delta steel by 3, because this length is 3, or delta aluminum is equals to 1/3 of delta steel. So, you can see now that we have one equation of equilibrium. Now, we have obtained another equation which we call, which is corresponding to the compatibility of the deformation, which we call as compatibility equation. So, equation 2 is the compatibility equation. Now, next thing which we will have to do is impose the constitutive relationship. That means, first we write this deformation in terms of strain, and that we relate to the stress. So, this if we write in terms of load and or rather stresses, we can say that P aluminum length aluminum divided by A aluminum times E aluminum. This is the deformation of the aluminum bar. This is equals to 1/3 of Ps, that is the load which is acting in the steel rod, times length of the steel rod divided by area of steel rod times modulus of elasticity of the steel rod. Now, if we substitute the values, we get P aluminum multiplied by length of aluminum is 1000 millimeter or 1 meter, divided by the cross sectional area of aluminum rod is 1000 millimeter square, times E, which is 0.7 times 10 to the power 5 megapascal. This is equals to 1/3 of P steel times length, which is 2 meters, divided by the cross sectional area of steel is 300 times 2 into 10 to the power 5. And this gives us a relationship that P aluminum is equals to 7 by 9 times P of steel. So, this is another relationship we got it from between P in the aluminum and P in the steel. And earlier we had one equation which is equation of equilibrium, which is P aluminum plus 3 times P steel is equals to 100. So, this is let us call the equation 2. So, from equations 1 and 2 we have then P s and 7 by 9 plus 1 or plus we have 3 of this is 3, this is equals to 100. We have P aluminum plus 3 of P s. So, P aluminum is 7 by 9 P s plus 3 equals to 100, which gives us the value of P s as 26.45 kilonewton. And from this the value of aluminum load in aluminum is equals to 7 by 9 times 26.45 and this comes as 20.63 kilonewton. And hence the once we get the load we can compute now the deformation once we know that the steel rod and the aluminum rod they are subjected to the load P s and P a l which we have evaluated now. We can compute that how much deformation this particular bar will undergo and how much deformation this bar will undergo. Now, since we are interested to evaluate the deformation of this particular point, if we know the deformation of this particular bar and from this triangular configuration we can compute how much deformation this particular point will undergo. Hence, the deformation of the steel bar delta S is equals to P s L s by A s E s, which is equals to P s we got 26.45 times 10 to the power 3 so much of Newton times L s which is 2000 millimeter and A s is equals to 300 times E s which is 2 into 10 to the power 5. Hence, this gives us a value which is equals to 0.882 millimeter. So, this is the deformation of the steel rod which is shown in this particular diagram. So, the deformation which we have obtained here delta S is equals to 0.882 millimeter. Now, from this triangular configuration we can compute the deformation of this particular point which is at a distance of 1 meter from here. So, the deformation of this is equals to 2/3 2 by 3 of this particular deformation. So, the deformation of the point where the load is acting, say delta at load point where 50 kilonewton load is acting, this is equals to 2/3 of 0.882 millimeter and this is equals to 0.588 millimeter. So, this gives us the value of the deformation of the load point, and this is what we were interested to know. We were interested to know that how much deformation this load point undergoes, and according to this calculation we find this is equals to 0.588 millimeter. Well, then I am sure that you could calculate the values. Now, you can check the values whether they are matching with this solution or not. Now, let us look into another example based on the aspects which we have discussed today, that due to the change in the temperature there will be deformation in the member, and that causes stresses in the member which we call as a thermal stress. Now, in this particular example it is stated that a bronze bar which is a 3 meter long bar, let us call this as AB. This bronze bar 3 meter long with a cross sectional area of 320 millimeter square is placed between two rigid walls. This is one wall, this is another wall, it is placed between these two, and at a temperature of minus 20 degrees centigrade there is a gap between the edge of the bar and the wall. So, edge of this bar and the wall there is a gap of 2.5 millimeter. Now, what we will have to do is we will have to find out the temperature at which the compressive stress in the bar will be 35 MPa. So, find the temperature at which the compressive stress in the bar will be 35 MPa. Given the value of alpha, which is coefficient of thermal expansion, as equals to 18 into 10 to the power minus 6 per degree centigrade, and the value of modulus of elasticity given is 80 gigapascal. Now, when the temperature goes up from minus 20 degree, now the bar is going to expand because there is an increase in the temperature, and when it will increase, when the bar will expand, since there is a gap between the wall and the bar, first due to expansion the bar will touch the wall. Till that particular time, since it is free to move, it will not experience any stress, but further extension beyond the touching of the wall, now the wall will not allow the bar to move. So, naturally there will be stress induced in the bar. Now, what we will have to find out is that now we can allow maximum value of this stress to go up to 35 MPa, and we will have to find out that temperature which will allow this expansion of this bar to cause the stress within this body as in 35 MPa. So, if we draw a free body diagram, then it will be easier to visualize that how the whole process is undertaken. Now, in such problems where we try to evaluate the stresses due to change in the temperature and where such restrictions are imposed, like the bar is fixed between the walls or the bar at this point is not allowed to go beyond certain value, we try to first remove either partially or the wholly the restrictions, allow the bar to move freely due to change in the temperature. We calculate that how much deformation it can undergo because of the change in the temperature, and then if there would have been restrictions, then to bring back to its that particular position, how much force we need to impose on that we try to evaluate, and that is what is the compatibility criteria. First we allow it to move freely, thereby there will be deformation because of the change in the temperature, and now we impose some external force to bring back that deformation to its original position, thereby how much force we need to put to bring back the member to its initial form. We evaluate that, and if we compare these two, from these we can arrive at an expression which we generally call as compatibility equation. So, that is what we need to do in this particular case. Now, we have the bar, and on this side it is fixed to the wall. Now, here we have one restriction which is another wall, but there is a gap between the wall and the bar. Now, when the temperature goes up from minus 20 degree to some value T, which we do not know, which we need to evaluate, initially when it starts expanding, it goes up to the wall without any problem until that time, since it is not experiencing any obstruction, the bar will expand freely, and thereby there will be strain, but there will not be any stress in the bar. Now, let us remove this, wall, and allow this bar to move freely, and because of the change in the temperature it will move. Of course, this is an exaggerated view. Let us say this particular expansion is delta. This delta, which is total deformation, has two parts. One is this initial 2.5 millimeter, which was unrestricted movement, and then subsequently it will be encountering the wall, and now since I have removed the wall, so this is also moving freely, and let us call this particular distance as delta dashed. So, delta, the total deformation, is equals to delta dashed plus 2.5 millimeter. Now, our job is to find out the temperature. Now, since the increase in the temperature is going to cause the deformation of the bar, we will have to find out now how much temperature we can allow, so that now that when it will be encountering this wall, it will be subjected to a compressive force, it will be subjected to a stress, and the restrictions imposed on this particular case is that the stress level can go up to 35 MPa. So, till the time it reaches 35 MPa, the temperature is allowed to increase. As soon as it goes to 35 MPa, we cannot increase the temperature further, because then the material may not be able to withstand that amount of increase in temperature. So, to do that, that means when I have removed this wall, when I have removed this particular wall and allowed the bar to move freely, so naturally the second consideration, which is realistic situation, is that I will have to apply some force on this bar and bring back this deformation to this particular state, so that the member is between these two walls. So, that means this additional deformation delta dashed, which is getting caused from the wall to this end, has to be brought back to this particular position, and for that I will have to apply a load P, and this load is going to cause a stress in the bar, which is equals to P divided by the cross sectional area, and P divided by this cross sectional area, the stress is to be limited to 35 MPa, and under that consideration we will have to find out what is the value of capital T, so that the stress level is exactly 35 MPa. So, if we now calculate the compatibility equation from this particular concept, from the concept of this deformation, if we now compute the compatibility criteria, then what we can do is the delta is equals to the deformation which we are getting in the bar, which we have designated as delta, is because of the change in the temperature. Now, initial temperature was minus 20 degree, the final temperature is capital T. So, the delta T, the change in the temperature, is equals to T minus 20. So, this is equals to T plus 20. So, this is the value of delta T. Now, as we have seen that strain epsilon T is equals to alpha times delta T, or deformation due to change in temperature, which we have called as delta T, is equals to alpha times delta T times the length L. So, in this particular case, the coefficient of thermal expansion, which is given as 18 into 10 to the power minus 6 per degree centigrade, multiplied by change in temperature is T plus 20 times L is 3000, the original length 3 meters. So, this is equals to delta, which is delta dash plus 2.5. So, this is 2.5 plus delta dash. Now, from this we get the value of delta dash is equals to 54 into 10 to the power minus 3 into T plus 20 minus 2.5. Now, this delta dash, which is being caused from the wall to this end, and this particular part has to be brought back to this wall level by applying this force P. So, this delta can be written as PL by AE. By the application of external force P, we are bringing back this delta to the wall position, and P by A, P divided by the cross sectional area, we can write this as stress. Based in this particular problem, since the stress is limited, we write this expression in terms of stress. So, P by A is the parameter sigma times L by E is equals to this particular quantity, which is 54 into 10 to the power minus 3 times T plus 20 minus 2.5. Now, from this we can compute the value of T. Now, sigma is given as 35 MPa, and the length now, since initially it was 3 meter and then we have allowed it to move because of the increase in the temperature, and since there was a gap between the wall and the bar of 2.5 millimeter, and this 2.5 millimeter movement is unrestricted. So, the stress start getting generated only when the bar starts the wall. So, the length which is going to cause the stress, or which is going to cause this additional deformation, is equals to 3002.5, means 3000 plus 2.5 is the length. This divided by E, which is 80 gigapascal here. So, 80 times 10 to the power 3 megapascal, and this is equals to 54 into 10 to the power minus 3 times T plus 20 minus 2.5, or if we evaluate this, it comes to that 1.3136 plus 2.5. This is equals to 54 into 10 to the power minus 3 times T plus 20, and then T plus 20 from this expression is equals to 70.62. If we compute this, you get this as 70.62, and hence the capital T is equals to 50.62. So, if the temperature goes up to 50.62 degree centigrade from minus 20, then the bar will be experiencing a stress of 35 MPa. So, that is the problem, that if you allow the bar to undergo a change in the temperature from minus 20 to 50 plus 50.62, the bar will be experiencing a stress of 35 MPa. But the interesting part of this to be noted here is that this value of T we have arrived at from the criteria where we have equated the deformation part of the bar. Initially, we have allowed the bar to deform in such a way that it undergoes movement freely over that 2.5 millimeter, and then it goes and hits the wall, and then it keeps on increasing because there is a change in the temperature. But when it is giving a thrust on the wall is giving a reactive force, which is causing an internal stress in the member. And so, we have derived this equation based on the deformation compatibility, which we call as the compatibility equation. And so, the change in the temperature is basically an indeterminate system, and we solve the problem in terms of indeterminate form. Well, let us look into another example where a rigid block of mass m is supported by the 3 symmetrically placed rods, and the ends of the rods were level before the block was attached. They were in the same level. Now, you have to find out, you will have to determine the largest allowable value of m that can be this bar can carry. The cross sectional areas of steel and copper rods are 1200 and 900 millimeter square. Then modulus of elasticity of steel is 200 GPa, modulus of elasticity of copper is 120 MPa, and permissible stress for copper is 70 MPa and that of steel is 140 MPa. Now, these are the two copper bars, and this is the steel bar of length 240 millimeter and length of the copper bar are 160 millimeter, and they are placed at 1 meter interval, symmetrically placed. So, before this block was placed, they were on the same level. Now, after the block is placed, they will undergo deformation. Now, what we will have to find out is that how much is the weight that we can put, so that they are within their stresses do not go beyond these values. Now, first let us write down the equilibrium equation. Now, this is the bar or the block whose mass is m. So, the load that it transmits on those 3 bars is equals to the weight of it, which is m times g. Now, we have the 3 bars placed, central one is the steel one and 2 copper rods. So, let us call the load that will be carried by steel rod is Ps and those of copper by Pc. So, we can write down the summation of vertical forces 0 will give us W as equals to Ps plus twice Pc. So, this is the equation of equilibrium. This is the equilibrium equation. Now, the compatibility equation, next equation which we will see here also you see unknown parameters are Ps and Pc, and of course, we will have to find out W in terms of this. Now, we need another equation which is in terms of its deformation compatibility, and since the block is placed when the bars were uniform and it is expected that it will be in the same level. So, the strain in the copper bar or copper rods will be equals to the strain in steel, or the deformation that the bars will undergo. The deformations will be such that the strain in the steel bar will have the same value of the strain in the copper bars, and this leads us to the criteria that if we substitute the values of the strain, which is P c times L c by A c times C c, C suffix stands for copper, is equals to P s L s by A s E s. Now, this gives us a relationship from which we get P c is equals to 27 divided by 40 times P s. And if we compute the value of W in terms of P c and P s, now here another criteria is to be noted that the maximum value of P c and P s can be evaluated from the given stress. Since the allowable stresses on these rods are given, so the maximum load that the rods can carry is equals to the stress in the rod multiplied by the cross sectional area. So, the value of P s is equals to the stress in the steel rod multiplied by the cross sectional area of the steel rod, and the maximum load that the copper rods can carry is equals to sigma c times A c. So, from this we compute the value of W, and from the criteria that from the maximum value of steel rod, if we compute, we will get W as equals to 789.6 kilonewton, or mass we get around 80.6 10 to the power 3 kgs, whereas from the other criteria, from the limiting criteria for P c, we get mass as equals to 22.6 into 10 to the power 3 kgs. So, since we are getting two values, and out of this is the lowest one. So, that is the maximum value that we can apply, beyond which if we apply that, the values of stresses in the bar will not exceed the permissible limits. Well, then we have another problem, which is similar to the previous problem only. What we will have to do is we got to determine the lengths of the two copper rods, so that stresses in all three reach their allowable limit simultaneously. Now, in this case we are allowing the stresses in the bars to reach to their limiting values simultaneously, then what should be the length of the copper rods? Now, this is given to you, you solve it. Next time we will discuss about this particular problem. Also, we have another problem which are related to this thermal or temperature changes in the member, that all members of the steel truss shown in this figure have the same cross sectional area. Now, if the truss is stress free at 10 degree centigrade, now determine the stresses in the members at 90 degree centigrade. For steel, alpha is equals to 11.7 into 10 to the power minus 6 per degree centigrade, and E is 200 GPa. So, to summarize, in this particular lesson, we have included the concept of strains due to change in temperature, we have included the concept of thermal stresses, we have seen the steps to evaluate unknown forces for indeterminate systems, and then we have looked into some examples to demonstrate the evaluation of stresses due to change in temperature. Now, we have some questions for you, which are: what are the steps for the evaluation of unknown forces for indeterminate systems? What is the expression for thermal stress? And is the evaluation of thermal stress in a stressed body a determinate one? Look into these questions. You will have the answers in this particular lesson itself. We will be discussing these answers next time. Thank you for your attention.